Here's a question that sounds stupid until you actually think about it. Could you build a staircase to the International Space Station? The ISS is only 408 kilometers up. Engineers build things. Stairs are one of the oldest structures in human history. So let's take this completely seriously, do the actual structural engineering, and find out exactly where and how badly it goes wrong. The answer, it turns out, is everywhere. But let's be specific. First, let's establish what we're building. A standard staircase has a rise of about 18 centimeters per step. To reach 408 kilometers, you'd need roughly 2.3 million steps. That's a lot of steps, but it's just a number. It doesn't tell us anything about whether the structure can stand. For that, we need to think about the column. Because a staircase to the ISS isn't really a staircase, it's a column, a 408-kilometer tall column with stairs wrapped around it. And columns have a specific, well-understood failure mode. It's called buckling. Buckling is what happens when a column gets tall enough that it can no longer support its own weight in a straight line. It bends slightly, and then that bend accelerates, and then the whole thing is a very fast, very expensive pile of debris. The critical buckling load, the point at which this becomes inevitable, depends on the material, the cross-section, and the length. For a 408-kilometer column, the length term in that equation is doing an enormous amount of work.
Let's try steel. Steel is what we build things out of when we want them to be strong. The Burj Khalifa is mostly steel. Its core column is about 0.83 kilometers tall and required careful engineering to keep it from buckling under its own weight. We need something 500 times taller. For a steel column of sufficient cross-section to theoretically support itself that height, you'd be looking at a structure so wide at the base that it would cover a significant portion of a U.S. state. And it would still buckle, because the weight of the steel itself, 408 kilometers of it, would exceed the critical load before you got anywhere near the top. So steel doesn't work. Let's try carbon fiber, which has an extraordinarily high strength-to-weight ratio. It's used in aerospace applications precisely because it's strong and light. With carbon fiber, the numbers improve considerably. The base footprint shrinks, the buckling threshold rises, and then we hit a different problem entirely.
The atmosphere. At 408 kilometers, you are well above the atmosphere, but between the ground and the ISS, you pass through every layer of it. The troposphere, where weather happens, the stratosphere, where jet streams live, the mesosphere, where meteors burn up, and the thermosphere, which sounds warm but is technically almost a vacuum. Each of these layers has wind. The troposphere alone regularly produces winds exceeding 200 kilometers per hour in jet streams. A 408-kilometer tall structure in a jet stream is not a structure. It's a tuning fork. Structures oscillate in wind. Every tall building does this, and engineers design for it carefully. The Type A 101 skyscraper has a 660-ton pendulum inside it, specifically to dampen wind-induced oscillation. Our staircase would need the equivalent of a 660-ton pendulum for every few hundred meters of height, which gets complicated quickly. And also, each pendulum is itself subject to wind, and we're only at kilometer 3.
Let's assume we solve all of this somehow. Exotic materials, active dampening, a base the size of Texas. We built the staircase, now someone has to climb it. At sea level, the air pressure is about 101 kilopascals. At 8 kilometers, the height of Everest, it's dropped to about 35. At 18 kilometers, it's under 10. Above roughly 19 kilometers, you enter what's called the Armstrong Limit, the altitude at which water boils at body temperature. Without a pressurized suit, your blood begins to vaporize. This happens at step approximately 105,000 of our 2.3 million step staircase. So our climber needs a spacesuit from step 105,000 onward. Fine, spacesuits weigh about 130 kilograms on Earth. Climbing 2.2 million steps in a 130-kilogram suit is, conservatively, an athletic challenge. Above the Armstrong limit, we also lose convective cooling, the mechanism by which your body dumps heat into surrounding air. In the upper atmosphere, there's not enough air to dump heat into. Our climber is now in a spacesuit, on a staircase, slowly cooking.
And then there's the small issue of the ISS itself. The ISS orbits at 408 kilometers, but it is not stationary. It travels at 7.66 kilometers per second, roughly 27,600 kilometers per hour, completing an orbit every 92 minutes. The top of the staircase and the ISS are almost never in the same place at the same time. So, to summarize, the structure would buckle under its own weight, the wind would tear it apart at kilometer 3, the climber's blood would boil at kilometer 19, and at the top, the ISS would not be there. But the stairs themselves would be fine. Structurally, stairs are a very mature technology. We've completely mastered stairs.